with an announcement, which Tom reminded me to make. So in 2027, there's going to be a KITP program on these energy correlators plus detector operators, trying to get both people from the more formal side and the more phenomenological side. And so this is organized by myself, Tom, Alexander Homrich, and Sasha. And so January 2027 may seem like a long time, but the deadline for this is October 5th. I think it's a floating deadline, but so if you're interested, you should apply for this. Great. Okay, so now we can continue on. So just as a 30-second reminder of what we went through last time, so I tried to describe why one might be interested in a slightly different class of observables, which are these correlation functions of detector operators, which measure kind of different fluxes of different quantities at infinity. And we went through how you could define several different ones and compute them in either theories with a gap or without. And we wrote down, in the case of the CFT, this kind of nice energy detector operator, which we showed here, which is an example of this light ray operator. And then we did some kind of very boring examples of just computing, for example, the 1-point function of this in some scalar state, which just gave some very simple answer. And so this was just meant as a warm-up, because this is very boring, both from the perspective of the CFT side, because this is just related to this 3-point function. But this is also not very interesting from a kind of collider perspective, because the only thing that this is telling you about the state that you've injected is just the total energy, which is conserved, and so it's not really telling you anything. And so in particular, what you'd like to be able to do is to start to measure higher point correlation functions, which can distinguish, for example, between theories that produce kind of many particles or kind of sprays of particles collimated in different directions. And so these states both have the same total energy, but they'll be distinguished by their higher point correlation functions. And so what we want to do today is to start exploring these higher point correlation functions. So in particular, the next one beyond the 1 point, and I'll switch this marker. The next one beyond the 1 point is the 2-point correlation function. And so one knows that this is going to be much more complicated, because in particular, this is related to a 4-point function. So if I want to compute this from a correlation function of local operators, this is related to a 4-point function, so it's actually going to have some non-trivial information. And so the way that one should think about this, and I'll show some animations later, is one is putting two detectors at two different angles, like this, and I'll always, so they have some angle between them, and I'll generally express this in terms of this particular variable, which is 1 minus cos theta over 2. And so in general, one could also do this in some more complicated non-scalar state, where it actually depends on the individual angles n1 and n2, but here I'll just simplify this to the case where it really just depends on the dot product between the two. And so what one would like to be able to do, so this for physical kinematics goes between the z variable of 1 when the two detectors are exactly back to back with each other, so when they're separated by pi, and the z to 0 limit where the two detectors are really kind of brought together on top of each other. And so what we want to do today is to try and understand kind of what the shape of this curve is in different theories, and also in particular, so this is generic, or this is a function of kind of two cross ratios. And so one would like to understand kind of what physics of this 4-point correlator is kind of projected onto this thing which you can actually measure in experiment, and how you can kind of use known properties of this to understand this. And so just as a kind of historical remark, so this object, when you have two of these, is called the energy-energy or correlator, or EEC. And so this was introduced, I think, around 1978 or so by Basham, Brown, Ellis, and Love. And then people worked quite hard, even in the kind of early days of understanding these two different kinematic limits, which I'll discuss in a bit. And so this one was first understood to some extent by Parisi, and this one was understood by Veneziano, Konishi, and Yukawa. And so people have been trying to understand these kinematic limits and compare with experiments for quite some time. Okay, so before going on to actually calculating this, it's nice just to get some very basic intuition for the two kind of simplest possible cases of what this distribution could be. And then we'll move on to actual interacting cases. So the kind of two limiting cases which one can have in mind. So the simplest thing for understanding this is to begin by just taking a free theory so that we can actually compute things. And so if the theory is free, the only thing one can do is to change the source which is producing the state. And so it's nice to consider two source operators. So the first one can just consider some phi squared. Again, just in a free theory, and so what this does is just to produce, so it's just some form factor which produces kind of two particles going out. And then one can also consider, and this relates a bit to the question last time about considering heavy states, one can also consider some operator phi to the k, where k is much, much bigger than 1. And so in this case, instead of just producing, or the form factor injecting kind of two states, you have something where it injects kind of many, many particles directly out of the form factor. And so again, here we're really just doing a free thing, so there's no interactions, and so just whatever comes out of the detector, or whatever comes out of the form factor just goes into the detector. And so for these two cases, it's a very simple exercise in kind of Wick contractions to just compute what this correlator will be like, but you can also just immediately kind of write it down intuitively. So what's happening in this center of mass frame, in which I'm always considering this two-point correlator, is if I just have these two particles coming out, so they go like this, and then there's two configurations where this can overlap with my two detectors. So there's one where I have one detector over here and one detector over here, and then there's a second configuration where this one particle, or I have my two detectors exactly on top of each other, and this particle goes through both detectors. And so in this case, what one gets for this distribution, and I won't normalize it, is a delta function, or is just a sum of what are called contact terms. And so it's just two delta functions situated at the two kinematic limits. And so this is good as a kind of reference for an extreme of a kind of just free theory, that you just get two delta functions at the two kinematic limits. The other case, when you have many, many particles like this, again, one can guess very easily the leading term. And so in this case, instead of having these kind of delta function distributions, what you're going to get essentially as I take the infinite k limit is just a kind of uniform distribution of energy. And so in particular, what one expects, or what one can show, is that this starts with 1, and then you have terms, and so these were computed, and it's a nice exercise to compute them. And so you get some particular form like this. And so this gives another kind of extreme limit, which will be useful in a number of the theories when we actually compute them, because they'll kind of interpolate between these delta functions and this kind of uniform distribution. So if I draw this, this will be something essentially completely flat as a function of angle. And just as one kind of side comment, so you can also get this very similar behavior. So you can also compute this, for example, at strong coupling in n equals 4 using ADS-CFT. And so there you get a very similar behavior. And so I'll just write it for reference. So you again get this 1 as the leading distribution. And then you can tell that there's a difference between this kind of spray of particles and just kind of a uniform mush, because you do not have this contact term shown here. So these kind of contact terms occur when you have actual kind of particle excitations, whereas if you do this in some strongly coupled theory, what you get is this, plus high. So where this is an expansion in the strong coupling limit. And so just as one side note, so all of these satisfy kind of some rule or Ward identity, where if you integrate them from 0 to 1, you get back 1 in some units, which is just saying that it goes back to reproducing the total energy that was reproduced. And so now what we want to do is to actually start considering interacting theories, which will have a kind of more interesting behavior. And so before I show, and I'll start by showing the kind of results for QCD in a second, but I just wanted to first highlight kind of these two limits and why they're interesting. So I'll just kind of add onto this drawing.
Sorry.
Yeah.
So for that very first, very simple example,
yeah.
So you have two delta functions, but
yeah.
in one of them you kind of only pick up half the energy. Is that?
Yeah. So I didn't work out the factors, but so each one is
factor?
weighted by the EIJ, which has a factor, but then I have a permutation, and so what you actually get is a factor of 1/2 like this, and then that satisfies this sum rule. Yeah. So each one, so you have like
but they
Q.
have equal weights. There's no relative.
They have equal weights. Yeah.
Sorry, in the same setup, if it was not free theory, but like some integrable theory, how does this picture change?
If it's so we'll show a whole bunch of examples in a second. So hopefully that will, if you still, so what I'll try and do, I'll go through n equals 4, QCD, AVJM, and gravity, and so hopefully you'll see how they kind of, if it's still not clear at the end, yes.
And are you always in the rest frame of the momentum of the source?
Yeah, so I'll always inject just a momentum into here, so my Q I'll always take to be like Q0, 0, 0. Just for simplicity, yeah. Okay, so generically, as one goes to different theories, one expects interesting behavior in these two kinematic limits, which I've highlighted here. So one is this Z to 0 limit, and one is this Z to 1 limit. And so the reason why one expects some interesting behavior in the Z goes to 0 limit should be kind of obvious from the setup that one is having, because this is where you really bring the two detectors on top of each other. And so as I'll describe in more detail a bit later, so the way that one should think of this is one is really bringing these two detectors, which I'll draw as these two lines shown here, these two light rays that are separated by some angle theta. And so one is really bringing these on top of each other. And so in this region, one expects that there should be some form of operator product expansion, which I'll discuss more later, where you can kind of expand, and this is very, very schematic. You have essentially a twist expansion in some other set of light ray operators shown here. But here you expect something interesting, because this is really where you're bringing the two operators together. So the other place where you actually get something interesting, which may be less familiar from the detector kinematics, is when you bring the two operators to this Z goes to 1 or this back-to-back limit. And so depending on if you're used to thinking about these things in the collider frame or not, I just wanted to describe why this is an interesting limit from the perspective of the underlying correlator itself, or just to show kind of what properties of the correlator it is actually probing. And so the easiest way of understanding what is happening in the back-to-back limit is to first go to Mellon space. So if you want to look at the back-to-back limit, what we can do is we can first look at the underlying correlator, and I'll just write it as phi of u and v, and we can Mellon transform this. Like this. And instead of looking directly at the distribution of the energy correlator, it's nice to look at its moments. And so in particular, we can look at moments with respect to Z, which I'll denote like this, which are just integrals from 0 to 1. Like this. And so in particular, the kind of behavior as Z goes to 1 is kind of imprinted in these in the behavior as n goes to infinity. And so what you can do is you can kind of swap the order of integration, and what you get out is that you can write this in terms of, and I'll just, because you don't want to see me write them all out, there's a bunch of gamma functions. There's kind of some block of gamma functions of j, which don't really matter for now. So I'll just, it's not really important. Like this. And so now what we can do is just expand this out in the large n limit. And in that case, you actually get a very simple expression. And so this just goes like, again, this. Like this. And so if you compare this expression with this expression up here, what you see is that this is really probing the correlator in the limit where u and v go like 1 over n. And so in particular, what you're probing in this back-to-back limit is the kind of light cone limit, or the limit where all the kind of edges of this correlator become light-like. And so while that may not be obvious, depending if you're used to thinking about colliders, that's the kind of piece of the actual correlator that one is probing. And so the way that one can think of this is you have your source. So the way one normally draws it, you have your two detectors like this. And so in this case, all these sides, like this, are all becoming null. And so in the kind of Penrose diagram type way of drawing it, what is happening is you kind of have your operator, your source and sink in the bulk, and you're having these kind of separations off to the detector, all becoming null. And so in particular in gauge theories, this will give a very interesting behavior in this limit, because these will essentially give rise to Wilson lines. But one can understand just from this picture that essentially in this back-to-back limit, you're probing this light-like limit or high spin limit of this underlying correlator. And so combining these two, this operator product expansion, which I'll describe, and this kind of high spin limit, it allows you to understand very nicely the kind of two kinematic limits, which we'll go through in different theories. So both, we can do kind of an expansion essentially about this end, which we can understand very well. We can do an expansion about this end, which one can also understand very well. And then in general, one doesn't know much beyond, for example, perturbation theory or something with what's going on in the middle. But if you're able to, for example, bootstrap 4-point correlation functions, it will give you the full distribution.
So when you write the 1-point energy correlator, you also, I mean, it doesn't matter for the scalar field, but for the ingoing fermion state, for instance, you also have the dependence with the kind of ingoing angle, which I guess also you could think of as beam, collider beam. And here you have like integrated over all angles, maybe,
Yes.
but does it sometimes make sense to consider also the dependence on the angle with respect to the collider beam? And
Definitely, yeah. So if I just have, so it depends, so there are two different cases which I discussed last time. So one is just if I have like some spin 1 source, for example, and then I consider this. And so in this case, I can do the exact, so this one I decomposed into essentially like a scalar part and a spin part. And so one can do the exact same thing for these higher point correlation functions. So you can just essentially, you can think of it now that there'll be kind of two angles. So one will be the opening angle between my two detectors, and then one will be kind of the overall angle. You can think of it as like the center of mass of the two detectors. And that is definitely something which is interesting to do and can be done experimentally. And then there was the other case, right, where you had, like I did it in the case of gravity, where you had these two colliding beams. And so the nice thing about this, if this is like a spin 1 source, the overall kinematic dependence is just fixed. So depending on the spin of the source, I just have some expansion in like cosines. Whereas in this case, I actually get, or what I showed in gravity, is you have a more complicated dependence on the dot product, for example, between the angle of the beams and this. And so in this case, it's definitely interesting to consider the full dependence, and there you really just have to calculate the full dependence. So it doesn't just trivially kind of decompose like it does in this case. And so in the kind of cases where I just have a local operator, it's just easiest to go to this simple case because the other pieces are just, you can just decompose them, and it's not that exciting. So that's why I'll restrict to this one. But otherwise, you just have you'd have some kind of function like, you can write it as some EEC of Z plus I had this term like cos squared theta minus a third times some like second function like this, and more generally you could expand. And each of these will be slightly different, and so I'm just focusing on this one.
Okay, another question. So you didn't consider just phi? The first example was phi squared.
Yeah, because so I'm always working in this center of mass frame where I inject just like this momentum, and so if I did that, I just have like the thing sitting there. If I really had a one particle,
So it's just delta of Z.
I don't even.
I mean, the 1 point works, so the 2 point should work, right?
But even in the 1 point, I wouldn't say it's delta of Z, right? If I really, and this, unless I boost, if I just shoot out the particle, so if I give it some momentum and shoot it out, right, I can do this, and I'll just get a delta of Z. But in this one, in this kind of one, it's kind of singular, because if I'm actually in this frame, the particle just kind of sits there and never makes it to my detectors.
But how come the 1 point?
But I would
Is
also say
non-zero.
in this frame, my 1.1 is also like, kind of ill-defined. I have to give it some momentum to kind of shoot it into my detector. So I can of course make it, I'm just restricting to this, but I can of course just like shoot it off like this if I give it some momentum, and then all of the n.1s are just delta of Z, yeah.
Okay, thanks.
Good. Okay, so what we would like to understand is how this kind of behaves in different theories and how one computes in these different kinematic limits. But first, to show that this is actually a kind of real thing, so there's both a video and then a measurement of what it is in QCD. So maybe if you can show the video. Yeah. Okay, so first I have to describe what is actually in this video. Okay, so what this is, so those two blue dots are the two detectors. And so this is plotted, so over there, it's plotted as a function of the angle between the two detectors. And so in QCD, because you actually have asymptotic states, right, what one is actually doing when one measures this thing is, I said last time, one could have kind of a sum over the form factor squared, which I'll write as a cross-section, and then I weight it by the angle of the two particles, and then I have a delta function of the angle that I'm measuring minus the angle between the two particles. And so this was imagining I have some complicated kind of spray of particles, and then I put my two detectors down as a function of this angle here. And so what one can now do is for every event, you can weight by this overall energy, which is how much that event contributes, and then you can kind of align the overall event so that they're centered and the two detectors are at those particular points here. And then with all the stuff kind of shown in the background is the other particles which are just coming off into the two events. And so you can see at the beginning, you're in this kind of collinear region as the two angles come very close together. And so that's why you have some kind of, so ultimately what is happening in QCD, as we'll show, is you kind of have two kind of sprays of particles like this. And so in the beginning of the video, you have the two detectors like this. So this is the beginning. And then the detector moves until it's over here. And then at the end of the video, you have the two detectors like this. And so that's why you can see these kind of two sprays of particles, or these two kind of hot spots. So right at the end of the video, you'll see it kind of forms into these two hot spots like this. And then what you get out is this kind of non-trivial distribution, which is kind of, it's peaked at the two ends, because that's where the kind of free theory or just these two delta functions would be, but it gives some non-trivial shape all the way throughout the bulk. And so then if one can show the first slide. Yeah. And so then the experimentalists can actually measure this extremely precisely now. And so this is what part of what we'll try and understand in the rest of the lecture by going through some different theories, is how to get to an understanding of this full curve in QCD. And so this is kind of illustrating these different regions, which I showed over here. And so in this central region, which I said was, we kind of don't have a kind of all orders way of understanding it. In this central region, you can really just do perturbative QCD calculations. So you can compute to whatever order is possible, like this. As you start moving towards this end, what you get is this high spin behavior, or this kind of light-like limit of the correlator, which I described before. And in QCD, this is described by the dynamics of Wilson lines. And so this will give this kind of double logarithmic behavior, or this logarithmic growth of the anomalous dimensions. And so that kind of turns this curve over, and that's what's in this kind of blue region. And then in QCD, what happens is at a low scale, it confines, and then ultimately you just have some hadrons which go into your detector. And that is where it goes onto this completely flat behavior, which is similar to this case, which I showed here, that at some scale you just have essentially free hadrons going into your detector. And then as you go to the other side, you first have some regime where the two detectors are kind of close, but still perturbative. And so in this regime, you have this kind of scaling behavior predicted by this light ray OPE, which I'll go through. Then you have some kind of confinement transition where you kind of turn from a perturbative scaling behavior. Again, you hadronize from quarks and gluons into hadrons. And then you again go to this kind of flat behavior on the left, where you're again in this regime here. And so it again just agrees with this kind of flat behavior. And so this, in the case of QCD, it's quite complicated because it really goes through all these different regions. But what I'll try and do is to kind of go into different toy theories which illustrate each of these regions in some detail. Yes. Good, so these are Wilson lines. So in the case of E plus E minus, where I have two quarks coming out, they're just fundamental Wilson lines. But this just depends on the, so if I had like a Higgs that decayed to two gluons, then I'd have adjoint Wilson lines. So it really depends on the kind of particles in my source. I'll go into this in a bit more detail in a second. Yeah. Yes. Yeah. Any more questions about this plot? Yeah. Yeah.
Sorry,
good.
Which ones you can calculate analytically? It's the two pink ones and the blue one, or what was
Yeah.
it?
So I'll show the calculations. I'll go through, and then actually maybe I can show this slide, and then that will hopefully, yeah. Good. So in the pink one, or the middle, the one that's labeled UV, so this one can compute in perturbative QCD to whatever order one wants. So that's really just a complete perturbative QCD calculation. And so as Slava asked, you have to add on some non-perturbative corrections, which are like you understand what they are. But so in this middle purple region, you can compute very nicely. In this big blue region, you also can compute very nicely. And so that is because you can compute, or you understand very well, these correlation functions of Wilson lines in QCD. So this one can compute very nicely. And here I'll explain why. But so in the perturbative calculation in this limit, you actually predict this turnover to flat. So that's something due to the logarithmic growth of the anomalous dimensions, you actually are able to see that in perturbation theory. And then the green is kind of a trivial, so we cannot compute, so In the green, it's really just like free hadrons, and so you can compute it in terms of the chiral Lagrangian or something, but it's just this case in this region. But we don't a priori know the kind of height, let's say, or the only way we can get the green is if we're at sufficiently high energies that we trust this turnover. Then we know that it just freezes out and goes flat. But there's a little bit of assumption in going from the blue to the green. So we don't know a priori that it didn't go so we can compute up this side, it turns over, we have control, and then we don't know that it doesn't jump to something like that. We don't, or that there's some kind of bump here, like that. So that's a kind of assumption in the, understanding there. So then as you move from the purple to this side, in the orange region, we have good control, and that can be perturbatively computed in terms of this light ray operator product expansion in its anomalous dimensions. And then there you actually have some non-trivial confinement in this purple one, and so there one doesn't know how to compute that from first principles. So you have to extract some non-perturbative information. So on that side, you then lose control.
Why isn't the light ray OPE z to 0?
It is, but the problem is, what happens is you lose perturbative control in a regime. So the difference, and I'll go through this in a second. So you lose perturbative control. So what these mu. So the problem is in the case of QCD, the scale you're probing on this side is the z times q squared, and on this side is 1 minus z times q squared. So as you go to very low z, you lose perturbative control. And so the problem is that the perturbative light ray OPE, because these are just kind of low spin and almost dimensions, in perturbation theory or in a CFT, it just kind of goes up like a power law, like this. And so you really need confinement to turn it over. Whereas the nice thing, or a feature of the back-to-back limit, which I'll describe in a gauge theory, is because of the logarithmic growth of the anomalous dimensions, it already turns you over in perturbation theory, and so you can push it further and then just turn on to the non-perturbative. But I'll describe, hopefully I'll make clear the distinction of why, in the case of so if you were in some theory that did not have a logarithmic growth of the anomalous dimension, then you have the same problem on both ends.
Okay, thanks.
Yeah.
Yeah. So I was wondering if this picture just changes trivially with the energy. So here is at 90 GeV. What happens?
Yeah, so here Q is at like the Z pole, so yeah, 90 GeV. So it changes in a slightly non-trivial way. So one thing which is a kind of a coincidence at this particular energy is that these two plateaus are of the same height. Right, so this plot, because it's, so one thing I should also emphasize is the way this is plotted is in a kind of double log scale. So on the left, it's like log of 1 minus, or sorry, on the right, it's log of 1 minus, and on the left, it's log of the angle. And so this emphasizes the kind of logarithmic behavior in both sides. And so as you scale the energy, what happens is that these two sides scale differently. And the reason for that is on this side, the turnover is really due to confinement, and so it's set by the scale lambda QCD. Whereas on this side, that turnover is really perturbatively computable. So it happens, as I'll show also in like n equals 4, so it has nothing to do with confinement. And so it doesn't move as much. And so what happens is these two peaks kind of go like this. And then if you went down to very low energy, it just essentially becomes flat. And so there's quite a non-trivial dependence on that as well. Yeah.
So just to understand the accuracy of the comparison you might expect, how big is the effect from the electroweak sector?
So tiny, yeah, really tiny. Yeah, so we actually, so one can add in like QED, it's quite easy actually to do, and we can add these in, and these are, so actually if you show the next slide, I can show the comparison, and so the QED corrections are like fraction of a %. And so they're very, they're very, very small. Or maybe if you can show the next slide. I think actually I have the, okay. Yeah, and so just to convince that this actually works, And so you can get a feeling of the level of precision that one can compare to. So now, because the original one is zoomed out a lot, and so I'll show how one actually calculates in these different regions, at least in toy theories. So in this middle region, right, so this is just, and this is a non-logarithmic scale. And so we'll calculate at least in n equals 4 the shape of this curve. And so this is just this region shown here, where you can compute things in perturbation theory. And so you can do it to relatively high orders. And so this overall, it agrees quite well. And you can see it's at the level of like 5%. So it's still much bigger than what you need for electroweak effects before they come in. So on this, this side is a comparison using the calculations of these Wilson line properties. And so fortunately, or in QCD, we don't have integrability, and so one can't do them to all loop orders, but we have the anomalous dimensions, which I'll describe what they are, at like 4 loops. And so you have quite good perturbative accuracy. And so you can see what happens is you start to see this turnover, and then I've kind of blurred out this final region where we lose perturbative control. So that's really where you hit the scale of lambda QCD, and also describe later the reason why we're kind of, or we're just computing it in terms of the Wilson lines. And so what happens at that scale is you really have just like string breaking of these, of the kind of flux between the Wilson lines, and so that kind of flattens it out, and our calculation is kind of pulling too hard. But overall, you again get quite good agreement on that side. And then on this side is where you expect this kind of light ray OPE behavior, and I've cut it off before it becomes non-perturbative. And this is just supposed to scale like a particular power law once it sets in, and you can see that it very nicely has this kind of power law behavior. And so, yeah, hopefully this answers kind of where you have control, and you can see kind of very clearly. One of the things which is nice is that when you plot just your perturbative answer, it's very clear kind of where it goes bad. And so it goes bad as you approach the kind of 2 endpoints once you get to a scale of order lambda QCD. But you can also see that the perturbative errors, or you kind of see this because it's just because the coupling is becoming very large. Yes.
Is the picture similar if you collide different particles in, so for example, I don't know, nuclei?
Good. So maybe a simpler question first is if I have different decays. So if I have like a Higgs decaying, what happens is that I get, because I have adjoint Wilson lines, these change the behavior of this particular peak. So there what I have is like a very gluon-rich final state. And so I get adjoint Wilson lines on this side, and then I get anomalous dimensions which are more associated with gluon operators on this side. And so there you get kind of different behavior of these two in a way which is very well under control. And so if when you mean if I collide like larger nuclei, if you mean that I really create like a quark gluon plasma or something, is that what you?
That's what I was.
Yeah. Okay.
I was wondering. Like,
yes.
What various possibilities?
Yes. So these have been measured in quark gluon plasma, and so what happens? So there's a kind of way of understanding it. So they've been measured primarily at small angles in the quark gluon plasma, and so kind of one way of understanding it is in terms of this light ray OPE. By evaluating it in some kind of, you can think of it also kind of like the OPE at finite temperature, is that it kind of just shifts the relative expectation values of the different operators. And in particular, what happens is it ends up enhancing higher twist operators, because these kind of see more of the medium. Or they're more affected by the presence of finite temperature. And so what you get in the, if you had the kind of left, or this collinear limit in some kind of quark gluon plasma state, is that at very small angles, it's exactly the same, which is kind of saying at sufficiently small angles, this OPE should be universal. And then what you get is, so if in vacuum, it's kind of like this. In the quark gluon plasma, what happens is you have some enhancement like this. And you can, in general, you can have some kind of more non-trivial shape, which you don't fully understand, but the kind of leading deviation from the vacuum one is some expectation value of these the twist 4 operators that are appearing here. And so this is kind of like, it's like the, OP at finite temperature that just kind of shifts things around.
Thanks. Yeah, so it's the small z and z close to 1.
So the z close to 1,
the
it will also
regions-
modify at finite
Yeah.
temp, and this has been less understood. Yeah.
Okay.
Yeah, and there's a kind of very, so there's a, like, so this is in terms of the OPE, but there's a very physical picture of what happens. So if I imagine producing some kind of like fireball that has some finite kind of size, which I would do in the quark gluon plasma, so as I measure my two detectors out here, like this, so in a kind of regime where the particles that are going into my detector are very high energies, I can really think of it as kind of producing kind of one particle, which then splits into my detector. And so if my two detectors are very, very close together, right, it's like the splitting or the kind of virtuality or the splitting appears very near to the boundary. So it's kind of like in ADS-CFT. And then as I pull these apart, it essentially pushes this kind of deeper and deeper into the bulk. And so then you see some transition where this essentially hits this. And so this is another way of understanding why there's kind of a difference between these two limits, is that this kind of, in this back-to-back limit, you're really probing the kind of underlying bulk operator, like in the center, and so this is what sets the Wilson lines. Whereas then in the collinear limit, why it's governed by this light ray OPE, is it's really just the kind of detectors which are living in infinity. And you're essentially kind of pushing yourself further into the bulk as you move the angle bigger.
Thanks.
Yes. So are there any more questions about this general plot before we kind of go through some examples of how to understand it better? Okay. So what I wanted to do is to just kind of go through, so the full calculation in QCD involves quite a number of pieces, and has kind of all these different behaviors, and so it's a little bit hard to fully understand. And so what I wanted to do is to kind of build up to it in three kind of different pieces, which illustrate kind of how you can have different behavior in this small angle and large angle behavior. And so the first one is is the case of a conformal gauge theory. And as I mentioned, in particular in this back-to-back limit, the fact that this is a gauge theory will be very important, and so that's why I will illustrate with that and highlight this. And so just as examples, I'll kind of show primarily n equals 4, but then also this ABJM at weak coupling, and then kind of how it interpolates to strong coupling. Then I'll show the case of gravity, just because it has a very different behavior in the two limits. So this is not helpful for getting from here to the QCD result, but it just kind of highlights how you can have a very different set of behavior in these two limits, in particular because gravity does not have a logarithmic kind of growth of or it behaves very differently in the back-to-back limit because you don't have this logarithmic growth of, they're not really anomalous dimensions, but you don't have a logarithmic growth. And then I'll kind of show how you can essentially kind of interpolate together these pieces to understand what's happening in a confining and asymptotically free theory, i.e. QCD, which I showed up there. Okay, so the first thing which I wanted to go through is to just go through the case of this conformal gauge theory. And so I'll first show what it behaves like at weak coupling, where one can really understand everything in detail. And then one can kind of, one can show the results at infinite coupling, and then you can kind of interpolate in between them by eye. And so for concreteness, I'll use the case of n equals 4 superhearing mills. And so as I mentioned kind of above, so in n equals 4 superhearing mills, if one computes this correlator, what you find, like this, is that at small angles it has this very nice power law behavior, like this. Then you have some regime where it looks exactly like QCD, and you can compute perturbatively. And then even though it's conformal, it actually turns over into this kind of flat region like this. And so then, and this is not normalized. I'll just draw it so that it aligns with this flat behavior here. At infinitely strong coupling, we have the behavior like this, so it's just a dead flat line. And so as I emphasized, the thing which is kind of interesting is that even in perturbation theory, you're able to actually get the same behavior in this particular limit. And then you can kind of draw some lines which interpolate between the two. And so what you expect is as you kind of increase the coupling, you just have something which kind of becomes increasingly flat like this. But in this talk, I'll only be able to show the kind of weak coupling perturbative results, and then I've already said that it's kind of flat at infinitely strong coupling. But very excitingly, so people can now actually bootstrap at finite coupling the 4-point, or at large n and finite coupling, the 4-point correlation function n equals 4, and actually produce these curves of this energy correlator at finite coupling, and it actually looks exactly like this, which is very cool. Okay. So now I just wanted to say a little bit about how one can actually do these calculations, and in particular emphasize the kind of behavior in this limit. And so for concreteness, so these are often computed, so in n equals 4, what I want to compute are, so I can have some scalar source, and then 2 stress tensors, like this. And so the nice thing about n equals 4 superheating mills is one can relate this, as long as these are in the stress tensor multiplet, I can just relate this to the scalar 4-point function of these 20 prime operators. And so this object is extremely well studied. So in particular, this correlation function, or as I said, it is now bootstrapped at finite coupling, but this is being computed, or many people have studied the perturbative structure of this correlation function, and in particular, its integrand is known as something like 13 loops. So there's a lot of perturbative data for understanding this object, and it's been studied extremely extensively. And so in particular, it's very nice that instead of performing some kind of phase-space integral, one can go directly from this correlation function to this, or to the 2-point energy correlation function. And so I won't show kind of all the steps in how this is done, but I just wanted to highlight some features of it to get a kind of feeling for what part of this correlator one is actually probing when one does this. And so as people may know, so if one computes this function at 1 loop up to some normalization, what you get is this famous Bloch-Wigner function. So at 1 loop, you get something, so it's some weight 2 combination of polylogs. So these are sometimes, depending on the literature, called either D functions or Bloch-Wigner, like this. And so what one would like to be able to do is to get from this calculation of the Euclidean correlation function to this particular object shown here. And so there's many different ways of doing this. So you can either analytically continue it and then actually take the integrals which define these 2 particular detectors. But there's actually a very nice formula which allows you to directly go from this object to the correlator up there. And so I won't derive this, but I just want to state it, and it also shows a little bit what, or it gives like a kind of little bit of an intuition for what aspects of the correlator one is actually probing when one takes this light-like limit. And so in particular, there's this nice relation that you can write the energy correlator as a form of discontinuity of this object over here. And so one can ignore for a second these epsilons, because this is just something for weak coupling perturbation theory. But you can essentially write it as some kernel times the double discontinuity about z equals 1 of the discontinuity about z equals 0 of your correlation function. And so I won't go through, because I just want to kind of highlight what comes out, and we can go through next time if we want. But the kind of important thing, or one thing, is one kind of tells from, for example, this, what parts of the physics of this correlator one is actually probing. And so one can also check, so what we'll see, so if you actually just stick in this object, it's very easy. So the only reason you need these kind of epsilons, which I put, is in weak coupling perturbation theory, you have some distributions which you need to be a little bit careful with. But otherwise, you can just kind of take this, and if you stick in this function shown here, what you get out is the first order in the coupling result for the distribution of this energy correlator, which takes this particular form shown here. And so if you plot what this looks like, it looks very similar to this kind of central region. So this, if you expand at small zeta to 0, this goes like, or some number over z. And if you expand as zeta goes to 1, this goes like a log, or like this. And so if you plot what this function looks like, it looks very nice over here. And then it kind of blows up like this. And so one can also just do some kind of sanity checks. So this object will in general be weight 2n at 2 loops. And so because you take 3 discontinuities and 2 integrals, you get kind of a weight, a single weight drop down to this logarithm down here. And so you can see that as compared to the full kind of off-shell 4-point function, this object is kind of a much simpler object. And so it's some kind of like projection of the total 4-point function, which can measure.
So question, do we know in general if this is always like a log type singularity, or like can you get to be a square root type of singularities in this limit, or is always like a log?
So you mean like here, if you always just have logarithms?
Yeah.
So in this 2.1, so in 4 dimensions, so I'll show in like ABJM, you can get more complicated things. But in 4-dimensional Yang-Mills, you'll just, in this limit, as you go to higher orders, which I'll show because one can actually, or one can do it, this is just, you just get, as you expand in this limit, it's always just higher powers of the log like this, yeah. And there's no square roots. Yeah, sorry, because there's like a bunch of, there's z and z bar in this correlation function, and so zeta is the like angle, like the physical angle, which is what I was previously calling z there, whereas z and z bar are the like cross ratios for the actual like local correlation function. Yes. Yeah, and so if you plot this, it just has this nice behavior, or so.
Sorry. How much does the fact that we're working with a planar gauge theory play a role here? Like, how is finite n supposed to change the physics here?
Good. So at weak coupling, it has essentially, so at weak coupling, it has no effect. And so there's some interesting, which is not understood as you go to strong coupling, what happens in this limit at finite n is not understood. But this I can do in at least at weak coupling, and I'll show in a second how one calculates this. At weak coupling, it behaves exactly in this way, regardless of what n one is at. Yeah. Yes. Any other questions? Okay. And so what one can see from this is, so you get essentially a very good, even if you just do it in fixed order perturbation theory, approximation for this collinear region. And so the reason why is that ultimately, as we'll show later, the full result in this limit is just a shift by a particular anomalous dimension, which at weak coupling is very small. And so this just kind of slightly changes from this particular power law shown here. But you can see that this behaves very differently from the picture which I drew here in the in this back-to-back limit, or in this large spin limit. And in particular, in perturbation theory, this just diverges like this, whereas the claim is that the claim is that the actual answer goes to a kind of flat value. And so, as was asked, if you compute to higher and higher loops, all that happens is you get logs to some power like this. And so all that happens is that the curve will kind of blow up or blow down, and you'll never kind of reach this plateau. And so what I want to explain a little bit is how you can actually, or because of the logarithmic growth of the anomalous dimensions, if you actually properly compute, you can get this behavior shown over here. And so one other thing which I should emphasize about this plot is so that this side is kind of generic in any conformal field theory, or at least weakly coupled conformal field theory. I'll have this. Whereas this side will really be specific to the case of a gauge theory.
So if you use like OP expansion of this 4-point function, is it this double discontinuity which kills all double traces, right?
Yes, exactly, yeah.
And then will it converge on the integral if you like split it, say, into domains or something like that?
No, it will not converge on kind of these ends. I think in the bulk you can get something, but on the ends it will definitely not converge. Yeah. But it will be an important, I'll make this point in a second when we consider, for example, the strong coupling limit, that the fact that you have this double discontinuity is what isolates these single trace operators. And so this gives a very different behavior as you go to strong coupling than compared to, for example, deep inelastic scattering, where you also have a very similar OPE of 2 insertions, but there you get the double trace operators, and so it behaves very differently. Good. So I think what I'm going to do, so next, I think for time, what I want to do is just give the result for this limit, and then next time we'll derive it in more detail. But what one can show is that, so in this particular limit, I'll describe a little bit where this comes from. So as in this limit where z goes to 1, you get some just generic function of the coupling. And in general, what this is actually related to is the OPE coefficients, or the squared OPE coefficients, for 2, in this case, of these O20 primes, and some high spin operator, I don't know what to call it, S, shown here, in the decomposition of the 4-point function. And then one has some integral times the cusp anomalous dimension, like this, plus something which I'll call B delta, which is just another function of the coupling, like this, times a single logarithm like this. And so just for reference, so if I consider in this case, the twist, or generically in this case is twist 2, but the twist 2 anomalous dimensions as a function of the spin, that these, in a gauge theory, these have a logarithmic growth with a coefficient, which is this cusp anomalous dimension, plus this constant term shown here. And so at least in the case of n equals 4, one actually knows these objects exactly to all orders in the coupling. And so I'll describe next time, I think, yeah, in more detail. You can get this in two different ways. One, by studying the high spin behavior of the OPE for the 4-point function. But there's also a kind of very physical way, which I'll just sketch now, because that gives some intuition for how this behaves. And so in particular, in the case, so I described that this particular limit shown here is when all these operators become null separated, like this. And so in this case, what actually happens, or the way that one should think about this intuitively at weak coupling, is I kind of shoot two very energetic probes, which go out into my detectors. These essentially source kind of Wilson lines or fluxes, which go along these directions. And then what I'm probing is kind of the essentially corrections to these Wilson line behaviors. And so of course these Wilson lines are also, or cusp Wilson lines are also described by these anomalous dimensions, gamma cusp and V delta, and at least at weak coupling you can kind of think of either high spin operators or these Wilson line operators kind of interchangeably. And so one nice feature, which I'll just, or when I come back to gravity, is the kind of Wilson line picture persists in gravity, whereas I don't know how to talk about these anomalous dimensions of particular twist operators in gravity. And so, and I'll derive this next time, but kind of one interesting feature of this formula is you can study the behavior of this object here, where now it's resummed through this exponent to all orders in the coupling. And so if you can just take the kind of saddle point, for example, as z goes to 1 of this whole particular object shown here, and if you do, you actually find that this behavior, or this object, goes like 1 minus z. And so it essentially, or it exactly cancels this 1 minus z, which is shown here, and leads to a flat behavior. And if you work out the prefactors, I forget exactly, but it kind of behaves like some e to the 1 over lambda, and there's some weird, or root pi over lambda functions like this. And so you can see that it's not analytic in the coupling, which makes sense because at any order in perturbation theory, and so, yeah, so what this is the actual height of this plateau shown here, as predicted by this formula. And so of course at any order in perturbation theory there is not an actual height of this plateau, but once you resum you get this actual result. And so this allows you to predict into this regime. And so the same will be true in QCD, that as long as you trust your perturbative expansion up to some particular scale, then it will allow you to turn over and give rise to this particular behavior shown here. And so just as a kind of, again, a remark, so actually Parisi derived some kind of variant of this formula in QED already extremely a long time ago.
So in which sense this integral is more precise than the saddle point of it, because anyway it's z to 1.
Yeah, so at z to 1, or so I'm just taking, so this I can just, yeah, I can just plot it exactly. This is just to kind of analytically, or to see whether it goes to what scaling behavior. So of course I can just plot exactly this function, but just to get the value at like, or just to see that it asymptotes to something flat, it's...
But then does this integral contain some corrections?
Yeah, absolutely, yeah. And so one should use, so this integral describes the full kind of turnover of this, and this is just because in this regime, it's really scaling like 1 or 1 over 1 minus z, and just to see kind of analytically that it actually goes to a flat behavior, it's just nice to take the saddle point, or just to kind of see that. But one should, of course, just really plot that full thing, and that gives this nice curve exactly like shown here. You mean, or to this whole formula? Yes, good. So there one expects that they're just order 1 minus z to the 0, which is why one gets a little bit worried, because now this has changed. So the non-trivial thing about this is it's changed the integer or scaling of this by a full integer. And so now you expect that in general you could have some offset to this value.
Sorry, so let me try this. And this formula, so it resums some stuff.
Yeah.
But this is only in the limit as z goes to 1, and the correction is 1 minus z to the 0?
Yes.
So how can you then trust anything if this thing itself is 1 minus z
Yeah,
to the 0?
I think you cannot really. You have to, because what's happening is you've identified the leading asymptotics of this behavior, which said it goes like 1 over 1 minus z. And then by doing the resummation, it's changed it by an integer power, right? And this is the same, it's kind of like in the light ray OP, when you have like twist 2 and twist 4, if things shift their scaling by an integer power, you cannot really trust it. And so to this full formula, there should be corrections of order 1 minus z to the 0. And so now that this has canceled, these are naively of the same order. So of course, in reality, or let's say at weak coupling, they are very suppressed because you get this, it kind of goes up for a long time. And as you can see that this one goes like this particular strange combination. So this one is very enhanced. But as you really interpolate from weak to strong coupling, it is not understood the role of these. Absolutely.
I see. So you expect that this correction that you just circled, it's not going to have like this e to the 1 over lambda type things.
I think it's not really, yeah, especially at finite, I think it's not. I don't want to. It's not really understood.
Right. But so you said that you can plot this at finite coupling. How does it compare? Is it?
Yeah. So I don't want to spoil, but you can take this formula, plot it at finite coupling at their Bootstrap, and it works beautifully. Mm-hmm. But it's very hard to know what these corrections. I mean, yeah, and it's not clear if how these depend on n. So I would say that, especially at finite coupling, there's very little known about this.
Okay, so the only formal conclusion we can draw from this formula is that it goes to a constant, but
yeah. So this one, okay. So all it is exactly is it goes to a constant, and that's why, like in the QCD case, when I said earlier, like we cannot rigorously justify that it doesn't go like this, and then you have like something like that. Or something, yeah, that you kind of have, or even just that it behaves like that. That one cannot. So it seems in practice that those corrections are small, and if you have some weak coupling regime, again that makes sense because you actually do get this 1 over 1 minus z scaling for quite a while, and then it kind of turns over. So these ones just go like 1 minus z, and so like if you do this in, so I didn't show, but so. We actually have a plot in QCD of the size of those smaller effects. So you have the curve like this, and then you have these ones that are constant, and they're growing and where this is like a factor of 100. Mm-hmm. But if you don't add any resummation, these catch up to here at it's like 10 to the minus 10 degrees. Where you should not be trusting it. But there is a real a problem as you go to very, very, very small angles, what actually happens. And in some sense, one can say that in QCD, we just get cut off by confinement before that, and then it's really free. And so we can kind of trust that interpolation a little bit better. But to actually, let's say if you want to compute the actual intercept here in, let's say, finite coupling n equals 4, I would say that is not, I mean, apart from, so they can do it with their numerics, but whether or not you have small corrections to this, is not understood how to do that.
Okay, thanks.
Yeah, and I'll show tomorrow, or when I actually derive this, you can see there's places in that derivation where you interchange limits and stuff, and it's a little bit fishy. And so that's a place where I think the actual Bootstrap results are extremely interesting for looking in particular at this region. Yeah, and I would say there's even less known at finite n, what happens. Because what's happening here, right, is in this picture which I showed, which is now horribly drawn. Right, you really have some kind of flux between these, but as soon as this can break at finite n, then you expect bigger corrections here. And so I say these are, yeah, not understood at all. But I think it's very interesting to do so. Yes. Good. Okay. And then I just wanted to make one comment. So this is kind of a, so one can do a similar thing just as a comment for ABJM. And so unfortunately, there's much less known about either the 4-point correlation function in ABJM, at least perturbatively, because you have to compute it to 2 loops to get anything non-trivial. And as far as I know, there aren't really explicit calculations of these 3-point functions with very high spin operators. But what one can do is or at weak coupling, one should have this picture of Wilson lines, and essentially all that happens in ABJM, or what one believes should happen, is essentially this just goes like a cosine, where you replace this b times the Bessel function by a cosine, and then you should get a kind of similar behavior, where instead of asymptoting to a flat curve, what actually happens, or what is believed to happen, is you have some asymptote to something that goes like 1 over square root of z. And so again, this would be very interesting to see. So then there you also know this gamma cusp and b delta from integrability. And so it again be very interesting to test these predictions as well as the 1 over n corrections to these. Okay, so I only have 4 minutes left. Okay.
Is this B some sort of impact parameter in the back-to-back limit or not?
Good,
really?
exactly. So this is you can think of it in the physical picture as an impact parameter. And so in particular, what it is it's like there's a separation between these 2 operators in this source, which is this B. So essentially they're separated in a transverse, and in particular this is a kind of, so the reason you get this Bessel function, at least in the perturbative regime, is because you do some kind of, it's like a Fourier-Bessel integral, and so it's really coming from this separation here between these 2 sources here. And that's why you can kind of easily go from 4 dimensions to 3 dimensions and at least make a guess for the behavior of this. And so then,
So I thought that you had a general argument that it had to flatten over near the right. So what went wrong with that?
No, but this is just there's no general argument that it should flatten. So that's in QCD, where it actually it's like gapped, it will always flatten there because it's just free. But if I actually have like a conformal field theory, it can just have some generic behavior there, and that generic behavior will depend on the particular dimension. And all that essentially, if you believe this kind of Wilson line picture, which you should have certainly at weak coupling, then you just essentially change the particular kernel here, and you can write this down in more general dimensions. And so it seems, in 3 it should just do something, and then you can adjust depending on the dimension. Sorry, Yes. And so then just in the final, so I'll go through these a little bit in more detail next time, but I just wanted to contrast this with one other example where you can actually, or where you have a different kind of behavior that is not governed by this double logarithmic growth. And so that's if you measure this 2-point correlation function, or not measure, but if you compute it in gravity or supergravity, so you can also compute this 2-point correlation function into some state of gravitons annihilating into another bunch of gravitons. And so there you get a very different behavior than in the gauge theory case. And so if you compute this like this, so in gravity, what happens is that at small angles, it's actually completely flat. And then you get a behavior that goes like 1 over 1 minus z if you compute it to first order in perturbation theory. So on this side, it really goes like 1. And then on this side, it really goes like, if you just do the same calculation which we did before at lowest order in perturbation theory, it goes like 1 minus z. And so in particular, the logarithm is missing. And so again, or in this case, you can understand the behavior in this back-to-back limit using, so you cannot really take, or you cannot really, at least as I don't know how to, understand this high spin limit of anomalous dimensions. But if you can compute it in terms of Wilson lines, and there what happens is the charge which you're coupling to, so you again have some Wilson line picture, like this. going into your detectors. But now in gravity, the charge that you're coupling to is just the kind of p squared, or the momentum of these lines. And so in particular, when they're null, you can think of it as essentially killing, so this leading cusp is proportional to the Casimir, or the charge of the Wilson lines. And so in this way, it just kind of removes this logarithmic growth. And so all you get is a kind of constant anomalous dimension. And what you get is that if you kind of resum this, it goes like some number times just, sorry, 1 minus some number times g Newton times the s of the collision. And so again, this at least has the correct kind of physical behavior that as I go to higher and higher collision energies, this should act to kind of flatten out this behavior. So as I go to higher and higher energies, it kind of just flattens out this behavior. But you don't have this double logarithmic asymptotics. And so this kind of agrees with the picture that at very high energies, you just expect some general kind of uniform spray of gravitons, which is coming out of your detector. And so again, since it's flashing red, what this also means that is in this limit here, which is governed by the light ray OPE, you have a very simple and non-singular behavior in the case of gravity. And so next time I'll go through in a little bit more detail these cases which I just described, and also how to understand, so I'll try and fill in how to actually do this light ray OPE and how to actually kind of derive this formula. Yeah, but thank you.
So about the Z close to 1 regime, I was wondering if there's any meaningful comparison with holographic QCD models.
With holographic QCD models?
Yeah, because typically they are not asymptotic free, but they get
the
right qualitative hadronic physics.
Yes. So, yeah, meaningful is a strong word. Yeah, so there's been some calculations. So I think it is definitely interesting to try. And there's been some calculations by like Chaba Chaki and his collaborators who have tried doing this in some kind of hard cutoff models. But there's some things which are kind of confusing, or one of the reasons why you kind of, or it's hard to access this actual kind of behavior is that in all those models, there's other kind of subtleties which I'm happy to discuss offline. But the one that is kind of very clear is that all of those are going from some kind of, you have some strong coupling, right, in the UV, and so you already have a kind of uniform distribution of energy, and then you just go to some hadrons, then it kind of hadronizes like this. And so the problem with this is that it can be very hard to see. So if this is kind of a uniform behavior, then I'm already flat, and then I just kind of go to more flat, but I've kind of transitioned from flat strong coupling to flat hadrons. And so it can be hard to understand what you're actually getting. And so what you'd really like is something that actually behaves in some asymptotically free regime so that I can have like string breaking and kind of have this, because the really kind of striking thing is the transition from this asymptotically free regime to the confining regime. And that is hard to get in any of these simple holographic setups.
Thank you.
But it would definitely be interesting to try, yeah.
Hello?
Yeah.
I don't have a blinking light. So would it be more realistic to consider non-protected operators to create states? And what is known, what will change in this integral?
Yeah, so I would say it is definitely interesting / more realistic. So one thing so there's been very little explored for generic operators. So they've almost all been in this case of these 4 O20 primes. There's also been some case of studying kind of like heavy protected operators. But other than that, very little is known. And that's part of the problem, in particular if one goes to ABJM, why you don't have all this high loop data. And so that's why you kind of don't have perturbative calculations there. And so people have mostly kind of, the reason why people have gone to this case is because it's easy and you can kind of probe the detector is in a nice way. But it would be very interesting. It would be very interesting to have that in particular, or for this ABJM case where almost nothing is known because everything starts at 2 loops. And there's a few of these 3-point functions. So like in ABJM, there's a few, as far as I know, up to like spin like 6 or something, which are computed. But then for actual like high spin behavior, like if it actually agrees, I mean, very little is known about this case, exactly because they're not protected.
So in the case of gravity, I suppose then when you go to high energies, you expect to go to this black hole regime where you form a black hole, and
yes,
you expect that to be flat?
Yes, I mean, that's a very, so if one believes, and so a lot of these, like when one takes these and kind of extrapolates from weak to strong coupling, you're definitely losing control. You're just kind of hoping that it's moving in the correct direction. And so in the gravity case, right, what you expect at very high energies is you just have some collision, you form some black hole, and you get many, many gravitons coming out, and it should be uniform. But of course, that is not what one is computing. We're computing some like perturbative 2 to n amplitude. And so you can see that it's kind of already behaving like this correctly in the collinear limit, just because you don't have collinear singularities in gravity. And you do have, so these are coming from so as compared to the gauge theory case, you don't get a double log, you just have a single soft emission. So these are just from iconal emissions. So they're kind of classical, which is why you can resum them. And here at least it's kind of moving it in the right direction, that as you resum these, you're just getting more and more and more soft emissions, and it's kind of lowering it towards this kind of flat behavior. But of course you can't really like resum your way here.
But is there a way to do an expansion starting from the large energy limit from the black hole phase, or you just have the leading term that you expect it to be flat, or can you do a bit better than that, some expansion starting?
Yeah, so that would be extremely interesting to try, and so I mean, almost nothing is known about these in gravity. So, I mean, other than these very recent calculations, nothing is known in gravity. So that would be extremely, extremely interesting to try. And I think one could do it, but just people have not.
So, at some point you said that the area for these curves should be 1, right?
Yes.
I'm a bit confused because these curves clearly have different area if I'm just lowering these curves.
Yeah, good.
Is it because of the contact terms at 0,
yeah, so it depends. Good. So in these, I've always like normalized some particular piece so that I can kind of adjust the behavior. But as you go in the coupling, you have both contact terms and just kind of overall terms in the bulk, which are changing. And so this has some actual slightly more complicated shape. But this is, this will just kind of lift up. So it's the same as in, this is definitely not an accurate depiction of what is happening in n equals 4. Like as you go to strong coupling, so if one drew it more realistically, the kind of strong coupling would be down here at 1, right? And this is extremely high and peaked. And so I've just kind of drawn them like this to show the alignment.
And as we interpolate in coupling, the weight of these contact terms at the 2 ends, does it change as well? Is it something,
so good.
or is
so
it purely a 3-level effect?
At finite coupling, you should not have any contact terms. And so you can see that like in resummation, you no longer have a contact term in this formula. So this really just gives a finite, there's no delta function. And you also, once you've done the resummation, you also don't have a contact term here because this is actually integrable. And so the contact term is really like a reflection of having like a particle excitation in your theory. And so even like in QCD, right, at finite coupling in QCD, the more accurate picture is you have this thing shown here. You don't have a contact term on this end because that would be like if you really had 2 like partons with a kind of Wilson line between them that actually made it to the detector as like partons and didn't hadronize. But you do have a contact term shown here because you have particle excitations. And so this contact term is definitely changing things as a function of both the coupling and the energy.
Because when things were flat, so when things were uniform, we knew the size, right? It's just energy over 4 pi, right?
Yeah.
So in that canonical normalization, can you say this 1, when you say 1, is it that, or is it much smaller than that?
Yeah, so this is, so part of the problem is in the gravity case, we also compute in some incoming state, and so we kind of fix some overall momentum. And so then one actually has to integrate over like the full collision to get back the actual sum rule. And so in this case, we don't have a strict sum rule because we're fixing certain kinematics. But this will be much smaller than 1 because you're getting a large contribution from this side. Yeah, so this is, Or
saying there is a plateau here, there is a plateau there,
Yeah, yeah,
but
yeah,
these
yeah,
plateaus
yeah, yeah.
could be super different.
Yeah, I think
right?
yeah, exactly. No, I think they're at very different energies, or at very different heights. Sorry, they're definitely at very different heights, and that's the same as like this plateau that one gets from the strong coupling or from the resummation is at a very different height than the strong coupling plateau. And so it's only kind of that it's getting the correct kind of physical behavior of flattening, but you're way off in the actual value. And that's because you just have an arbitrary function of the coupling multiplying it. So like in this formula, so this one is not known from integrability, and so you can just absorb anything into this as you adjust.
And we call it plateau because we like log plots, right? Otherwise,
Yes.
it's not a plateau. It's just it goes to a constant, right?
Yeah, but this, yeah. So we like plateau, or it's a nice word, but it's just a constant, yeah. Yes.
Okay, there are no more questions. Let's thank Ian again. And we reconvene at 50.
Okay, thank you.
Okay, everyone. So before we start with the talk of Yuan Xin, let me make a small announcement. So tonight we have the second social dinner. The place is Pede Manga. We will start at 7, so we should try to get there at 7, because at 7:30 you will be asked to choose between 4 dishes. They will take some time, so between 7 and 7:30 we should all be there, so let's be careful. There are various options to go there. Of course, you can go by metro, by Uber, but if you want to walk, it's a nice walk, it's a nice hike, takes 1 hour and a half if you run, 2 hours if you go take your time. And well, what we realized is that Google is giving you the bad direction. I mean, it gives you some geodesic, but it's not good. So it gives you to go, you are here in Pamplona, goes you go to Paulista, and then do some weird path until you get to the restaurant. Instead, if you go from Pamplona, you go straight ahead downhill, and then you turn left. At some point, you will reach the restaurant. So that's the good. Yeah. Yeah, yeah, it's like you have to follow this monodromy, right? Either you go this, or you go through the cut, and that's bad. That's good. That's good. Okay. So, okay, if there are no questions about this, we are very happy to have Yuan Xin here, and he will talk us about Yang Li quantum criticality. Please, thanks.
Thank you very much. Yeah, I'd like to thank the organizers to give me this chance to speak, and also thank the organizers for like holding such a beautiful event. So this is my third time in Sao Paulo. Now it's like, yeah, it feels like every time coming here is always nice, like meeting old friends. And in the future, I would like to hope to still work with, collaborate with all of you in the future. Yeah, so yeah, today I would like to share some interesting story about Yang Li quantum criticality. So hopefully it's simple enough. There's no subtleties like this. We will have to go to the second sheet to see the physics. So yeah, So this work is based on this our publication in May with Eric Argelio, our grad student who's really hardworking and talented, and Igor Klabanov, Grisha Tarnopovsky. And this is a coordinated announcement with 2 other works. So yeah, it's a day of 3D Yang Li. All 3 were published on the same day. One with Ruihuan, Dong, and Vishwanath, and the other one with Juan and Olivier. So all 3 work roughly tested the same criticality in the same set of models. But since it's a universality class, we can approach this criticality in different angles. So it actually, collectively, we got consistent result, which is a very nice check that the physics is correct. So today, I would like to roughly split the talk into 2 pieces. One is a brief introduction of what we know, including some history and the kind of procedure, how we are approaching this criticality from both classical and quantum approach. And then, I'll spend some time talking about numerics. Yeah, so let's begin with the history part. So the beginning of this story is many, many years ago, 1952, I believe. Li and Yang looked for the zeros of the partition function that is written in this way. E to the beta So it's a easing. So the partition of lattice easing model in the external magnetic field, and they studied this partition function in the complex in the in the complex plane of the external field H. So what they found is that if you go to the high temperature phase, so we have like Z2 preserved, and then study this partition function, they found zeros in the purely imaginary axis. And then as they like approach the thermodynamic limit in that like the lattice like denser, so the lattice is like size is larger and larger, you get like denser and denser zeros, and eventually these zeros becomes branch cut. And it's actually very easy to visualize and think about these zeros. So you take the absolute value of the partition function and then study it in, say, IH or minus IH. So if you take, okay, so at H is equal to 0, of course, this partition function is manifestly positive. And then as you take H to be larger and larger, eventually, like, so for purely imaginary H, this e to the H term is going to be a cosine and sines. So eventually, all of these terms, phase is going to start canceling, and you will have like zeros, some oscillations, right? And you can literally see this by just like pulling out Mathematica and code this up like a, say, 6-side lattice with like in one dimension, and you will see this these wiggles. And then, of course, if you take n to be larger and larger, then you will get like more and more of these zeros, and eventually it gets dense. But it's also, yeah, and it's also very, it's easy to visualize why the H has to be on the purely imaginary axis, because if you avoid this axis, have a little bit of real part, then these phases is not going to be exactly canceling. So you always have like a little bit residual imaginary part or a little bit residual real part. So what happens is going to be like this. So this is the raw picture. And this picture is turned into a theorem, or it's called Yang-Li theorem or Li-Yang theorem, whatever way you want to call it, that all zeros lie on the purely imaginary part of H, axis of H. And for a modern proof of this theorem, you can see there's a nice review by Cardy. Which includes the like a modern version of this proof, derived by somebody else. And then in 1971, Kortman and Griffith studied the same model, like the same partition function, using high temperature expansion. So this is the numerical technique. So you just like, okay, so you just expand this in beta to a certain order and keep all of the terms and study this thing. And what they got is that they showed that this the density of zeros approach a power law. Of course, if you lie exactly on the purely imaginary axis with this critical exponent, and they estimated in 2D the sigma is roughly minus 0.1 with some error bar they put. Sorry, what?
approach, the density approaches a power law, as what happens?
Away from the.
Well, you say it approaches, right? Approaches dynamic, like is a process. So
Yeah.
you change some parameter and then it approaches this power law, or what is the statement?
I would just say, okay, so I could ignore like higher orders of age or some coefficient. This is all I'm saying. So like. No, I think age is finite. Yeah. So. Yeah. So yeah. So age when age is above ih0 and close to this point. So this is h0. So you approach this point, and then in the vicinity of this point, above the first zeros, the density is gonna approach this behavior, a power law.
Okay, sorry, but then you are in some sort of thermodynamic limit already.
Yeah, yeah. So you need to go to the thermodynamic limit to see that the density of zeros grow too. But I guess you. Okay, so I'm not. I don't know the exact like what is been done in the high temperature expansion, but I would assume that you will.
I'm just asking because if you're in finite lattice, presumably there are just finitely many zeros, and I wouldn't know how.
Yeah. So you do see like discrete zeros, right? So you can literally plot this, right? So I'm not exactly sure what is the high temperature expansion, but for this you can literally plot it at 6 sites, and you will see this pattern.
Right.
Yeah.
But I'll have finitely many zeros there, and if I have finitely many zeros, I can talk about the density.
Yeah.
So I'm just asking basically where did the density come from? You took the thermodynamic limit, so there is.
Yeah, there are the more and more zeros, and then you can talk about like what is the number of zeros for a small section of age on this axis, and then you will get like a form. And then you can just do statistics, right? And then you get like that this behavior is going to be more and more smooth. Yeah.
But in the thermodynamic limit, is there what is the statement? Is that H naught is an accumulation point of zeros, or do you get?
I mean, it's like the density is like, so the zeros is dense on all this axis above H0. So H0 is the beginning of the branch cut, and beyond that is just all singularities.
Okay, thank you.
Yeah. So later, okay. So I'll talk about like later Fisher studied the same model, and he made it the analogy that the sigma should just be the magnetic critical exponent. So it has the same behavior, and the numerics supports that. Yeah. Questions? Okay, so yeah, so this is exactly what I'm gonna talk about next. Okay, so I erase this second sheet physics.
Just a clarification. So this you can do in any dimension? So
yeah, you can do in any dimension.
So even when the Ising model is actually mean field, you still have a non-trivial exponent for complex H? Is that the statement? Above 4 dimensions?
I haven't done it, so I don't know, but it's probably yes, because Ising, I mean, like, so Ising exists in all dimensions. Okay, so Ising as as an interacting CFT exists for dimension less than 4, right? But Yang-Lee exists for dimension less than 6.
Right.
So I would assume this is true, but since I haven't done it, so I don't want to make a claim. Yeah.
Thank you.
Yeah, so then 1984, Michael Fisher studied this Yang-Lee criticality, and he first found a field theoretic action. So roughly speaking, like how he got this action is by Hubbard-Stratinovich transformation. And the details is again written in this review. So roughly, you just find a Gaussian action of phi, a smooth field phi that, like, if you integrate out phi, you get back the same partition function. But if you integrate out s, then you get this. Then you get like some phi functional, and you expand the phi from as a power law, and you truncate that phi cube, and then you get this action. And you just assume that all the subleading terms, higher powers of phi, are irrelevant. And yeah. And then what he, so through this, he make a further claim that this density of zeros is analogous. So this power law of density of zeros is analogous to the magnetic field power law in the Ising critical point. So the magnetic field grows like the magnetization grows like some power law. So h minus IH0, and then you also have a critical exponent, and this critical exponent is going to have the same nature that under dimension analysis is delta phi over d minus delta phi. Delta phi is the dimension of the magnetization in Ising, and here the analogy is phi is the lowest primary, or the lowest local operator in the theory. Okay. Yeah, and then so with this field theoretic action, so phi cube becomes marginal at d is equal to 6. That means you can actually study the critical exponents in in 6 minus epsilon expansion, and he calculated things up to the epsilon square order, and he found that, and then there's some additional knowledge of this partition function is actually exactly calculable in 1D. So in 1D, you actually have exact result. So together with the exact result in 1D and the expansion to epsilon square order in 6D, then he cooked up a two-sided Padé approximant fit. And then the prediction is that is at d is equal to 2, you get sigma is roughly minus 0.15, and delta phi is roughly minus 0.34. And then eventually, we have exact result in 2D. Exact in 2D. And 1984 by BPZ, Belevin, Polyakov, and Zamolodchikov. That you have the minimal models and PQ. And P and Q are co-prime integers, and only the minimal model PP plus 1 are unitary, and all others are non-unitary. And in 1985, John Cardy made this identification that Yang Li in 2D is M25. So at this moment, we know everything about Yang Li criticality in 2D. What could, so first, why do people, why did he make this analogy? Because M25 is a minimal model with only one scalar primary. So for the chiral primaries are given by R and S. R is less than P, S is less than Q, and then you can, so only half of them are independent. So that means the table of chiral primaries, there's only 2 guys. One is 1, 1, the other is 1, 2. All the others are identical to these 2. 1, 1 is apparently identity with scaling dimension is equal to 0, and 1, 2 is identified as phi. And the scaling dimension, or the chiral scale, the chiral weight is -1/5. That gives delta phi is equal to -2/5, which is -0.4. So first of all, this is below the unitarity bound. This means the model is non-unitary. And second, this prediction is actually quite close to, well, quite close to the prediction done by Michael Fisher in the 6 minus epsilon expansion to epsilon square order. Let me see. So sorry, you're saying they're higher loops, or? Yeah. So yeah, this is, I'm only speaking of like the status of 1984. So later we're incorporating the 5-loop results.
Good.
Yeah.
Thank you.
Okay, so now this is roughly how people discovered and the Yang-Li criticality. And now let's just recap on what we learned for this exact Yang-Li criticality in 2D, and then hopefully we can generalize some of these knowledge to higher dimensions. Okay, I have until half an hour. So first, let's see the spectrum of 2D Yang-Li. So this is spin, this is scale dimension. We have spin 0, 1, 2, 3, 4. The unitarity bound is like this. So of course we're going to have identity. Put a star for anywhere we see primaries. And then at spin 2, we for sure will have the stress tensor. We have a primary that's below the unitarity bound, and it's identified as the phi operator. And after that, we have d phi, dd phi, ddd phi, and d to the 4 phi, all below the unitarity bound. And then, of course, we also have like d square box phi, box square phi, and d box phi. So all of these guys at higher dimensions. And remarkably, there's a TT bar operator, which is not null. And of course, so TT bar operator is just given by L minus 2, L minus 2 bar, Virasoro algebra acting on the identity. So the scaling dimension is exactly null, is 4. Sorry, delta TT bar. But one can ask in a more generic higher dimension, like what this operator is. So this action tells us that we will have an equation of motion that is roughly of the shape d mu phi is proportional to phi square, so that kills phi as a primary. So phi square is a descendant. So the leading the leading irrelevant primary would be phi cube operator. So this operator should be identified as the phi cube operator. It's a primary, and it's a scalar. And then we also have a Virasoro descendant L minus 4 plus 625 over 624. Then the exact number actually doesn't matter at all. I'm just writing it down for the sake of completeness. Minus 1 to the 4. So this Virasoro generator combination gives a quasi-primary in 2D acting on phi. And let's identify this as the Q operator, so I'm just giving it a name. And this operator is the next primary in spin 4. So here. Oh, I should put a star here. Yes. And then the scaling dimension of phi of Q would be 3.6. So 4 minus 2/5 is 3.6. And going to 3D indeed. This operator still survives. And we could ask, like in 6 minus epsilon weakly coupled expansion, or like what does it look like? It should be identified as phi d to the 4 phi operator. So one can study it, for example, using analytic bootstrap and ask, like, what is the anomalous dimension in the large spin expansion? Okay, so that gives us okay. So I'm already started filling up this table, right? So at d is equal to 2, all of the 3 leading primary operators at scaling dimensions are known, and now I'll resort to numerics in going to higher dimension. Yes, yes. Yeah, so all of these up to here, all of the guys that are not just total derivatives are all null. So it's a very sparse spectrum, which makes it easy to study in quantum Hamiltonian. Okay, so how do we approach the same quantum, the same criticality in? Oh, sorry. Before I do that, let me write down what we know about these scaling dimensions in higher dimension in 6 minus epsilon expansion. So we know delta phi up to epsilon to the 5 loop order, and then phi cube to epsilon 5. There actually is a work that calculate these to epsilon to the 6, but we haven't got a chance to like put this in our work yet. And this could be found in Borinsky's paper. And then for this Q operator, one can study its anomalous dimension. One can study this operator's anomalous dimension up to epsilon to the epsilon square order. And this is found in this paper. So once we have this exponential expansion, we could do a two-sided Pade. given that, for example, so two-sided pade, making the ansatz delta as a function of epsilon expanded to order mn is equal to sum j aj epsilon j to m 1 plus sum j to n aj epsilon bj epsilon to the j. And then fixing epsilon at epsilon is equal to 4 is equal to all of these 2D exact result. And at near 6D we have that, so fixing all of these parameters so that we have the same expansion. Then if you actually make a plot of, for example, delta phi 3 3, so what do you mean delta phi? Yeah. 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 Yeah, that's true. Okay, yeah, we haven't thought about that. Yeah, this is true. So we could do 1D and 2D constraint pade, and that gives us like one more parameter, and it's probably the plot is the prediction is going to be more accurate. Yes. Yeah. Thank you. Yeah, but even just fixing this already gives us like very smooth function at 2D and 3D, 4D, 5D, and 6D. So I'll just write at 3D the prediction is 0.218, and in 4D the prediction is 0.827, and then there are some higher D until you go to, okay, so let me just write it. And then eventually reaches 2D. So this is like, okay, so since the interpolation is so smooth, I think it actually have a chance that maybe this is true. Okay, so I'm filling some of these predictions, pade approximant on two sides using, I think all of these results are like 3 3, except for this is like 1 2. So these are our pade approximant prediction from 6 minus epsilon expansion. And then we'll go to the quantum criticality, and then try to measure these scaling dimensions, and we see agreements. So in 1994, von Galen wrote this Hamiltonian for 2D Yang-Lee criticality. Let me see how much time I have. Okay, 50. All right. Then for periodic boundary condition, I plus 1 is identified as 1, and then X, Z are Pauli matrix. And okay, I'll just talk about 2D and 3D at the same time because they're really similar. So the 3D version, which is fuzzy sphere, is given by, okay, So this is analogous to the ZZ, then plus R square, HX, psi dagger sigma X psi. This is analogous to X, IHZ, psi dagger sigma Z psi. So the idea is that, so this is IZ. So the idea is that, okay, so on a quantum lattice, we have this part being the transfer field Ising model, which has a critical point that goes to the 2D Ising CFT. And in this model, is okay. So on the fuzzy sphere, we just have like a bunch of fermions on some on a sphere, and yeah. So we have n fermions on the sphere, and the volume of the sphere is or the radius of the sphere roughly goes as square root of n. So on this manifold, there's some quartic couplings and quadratic couplings that it's like of the type current to current, and the current can carry a Pauli matrix sigma z or sigma x in analogy with the x and z Pauli matrices on the spin model in 2D. And likewise, if we only keep the top two terms in the quantum Hamiltonian in 3D, we also have a critical yeah, we can also reach the critical Ising CFT at the parameter v. Oh, okay. So at some parameter. So here I'm just using the U is an expansion of v0 plus some v1. So U is an expansion of some local expansion of the coupling between the current and the current, and we can expand this and ignore all of the subleading expansions. And so in the parameter of v0 is equal to 4.75, and hx is equal to 3.16, we have the Ising CFT in 3D. So this is a one-to-one analogy between each other. So now the idea is, yeah, above H is HS is equal 1. So the phase diagram is going to roughly look like this, the following. Sorry, this is HX. IHC, I don't need I here, just HZ. So there's a critical point, HX star critical Ising, which is 1 for 2D and 3.16 or whatever value according to your parameters. And we first go to high temperature. The high temperature phase, the Z2 preserving phase. And then we turn on imaginary coupling. Eventually, we hit the criticality. So it's going to look like this. So this is the Yang-Lee criticality. And then above which is what we call the PT spontaneous breaking. Let me explain to you what that means. Keep this. So remark number 1 The Hamiltonian is non-Hermitian, but PT symmetric. So PT is an operator that if you act on X, this goes to X, and then Z goes to minus Z. So this is like the Z2 flipping of the spin. But at the same time, you take the complex conjugate. So in the classical phi cube field, what it does is that it flips phi to minus phi. So let me just write it here. And then this PT, yes. Yeah. So all I'm saying is that there is an operator that takes a complex conjugate, and it's a Z2 kind of symmetry. All I need is that. Yeah. So whenever you have this PT commute with Hamiltonian, then and then PT squared to 1. Immediately you can derive that. So if you have an eigenvector of the eigenvalue E, then you can, since PT commutes with H, then you can derive that PT psi is another eigenvector of the eigenvalue E star, which implies that the E is either real or in complex conjugate pairs. So you either have real spectrum or you have complex conjugate pair spectrum, or both. And then remarks number 3, the eigenstates are bidiagonal. So now Hamiltonian is no longer Hermitian. That means like you're gonna have eigenvectors are not the same from the left and from the right, but you will have, for example, you have an eigenvector. There are eigenvector on the left, an eigenvector phi theta from the right, so yes, and then the orthogonality is not that you have psi prime. So this is not orthogonal, but psi dagger psi prime is always sorry, this is not orthogonal. So, but psi dagger psi prime is always orthogonal. So this is biorthogonal, and then since Hamiltonian, so written in this form. It's not real, but it's still symmetric, right? So the Z, X, Z like are all symmetric matrices, and just like some of the terms addressed by I is still symmetric matrix here as well. It's a symmetric but complex matrix. Then it's natural to say that psi theta is just the complex conjugate. So then it's natural to say that all of my matrix elements measured in the Young-Lee model is given by eigenvector transpose eigenvector. So I'm always doing this to measure the quantities. So when does the spectrum shift from real to complex conjugate? You could ask, on this axis, I'm always having a real spectrum because the Hamiltonian is Hermitian. And then as I turn on Z, it's going to keep real for a while because Z is small, but at some point it's going to hit a point, and then some real eigenvalues are going to be complex conjugate pair eigenvalues. So let me give you an example, very simple one-point example, one-side example. Just the Hamiltonian is equal to x plus IHZ. So if you make a plot of the energy eigenvalues, then you will have like at h is equal to 0, you have plus minus 1, and then they merge and form, I think this is a square root branch, there's a square root locally, and then becomes complex conjugate pairs. And this point is our PT spontaneous breaking point, and it's also the Yang-Li criticality. Because the gap closes, right? So in the thermodynamic limit, this point is actually going to be identified as the Yang-Li critical point since the gap closes. But it's actually an art rather than like, okay, so there's some science, but it's kind of like art, how to identify critical point at finite n because it just doesn't exist.
Sorry, can I ask why do you call this spontaneous symmetry breaking?
So if the eigenstates are in complex conjugate pairs, then PT flips one to the other, right? So then that means that each state is not a representation of
yeah,
PT.
that's true for literally every symmetry. Like, it doesn't
Yeah.
have to leave states invariant. If it leaves states invariant, then you just have a trivial action.
I mean, here PT acts trivially, right? So you can have PT odd or PT even. PT even really PT acts trivially, right? So it doesn't change the state. But here, the PT action on the state changes the state. So if this state is your vacuum,
If the state was vacuum, then I would agree with you. But
yeah. So this is what I'm saying, right? So if the vacuum does this, then PT is spontaneously broken. That's one, yeah.
so, but sorry, but I was under the impression that you just wondered if any state does this.
Oh, sorry. But I think, yeah, so I don't have a proof, but the observation is roughly all state break at once. Since the gap okay, so the physics, the following, so the gap closes, right? So we're actually gonna have a very dense spectrum near 0. So then all of these eigenvalues just gonna merge and collide and becomes complex conjugate pairs. All of the states that are eventually flowing into CFT will break at the same point with up to order 1 over n room.
Sorry, so you're saying at the critical point, all energies become complex.
Yes, but at finite n, we're not gonna see all of them hit the critical point at once. There's always like some hit first and some hit later, and it's kind of hard to decide what is exactly your critical point. But in the thermodynamic limit, up to order 1 over n, then yeah, you should.
But
yeah.
didn't you just give us estimates for the scaling dimensions which are real?
So we work on the real side, right? So basically, the CFT is on the side that is like a 1 over n split from the breaking point, where if you measure all of the spectrum, it gives you the CFT spectrum. So this works in 2D and 3D, and this is the how we identify the critical point and the critical spectrum. And then we extrapolate all of them to thermodynamic limit, and we saw that all of these identification of the critical point merge the same value. Yeah.
Okay, maybe we can discuss later.
Okay, so this is actually what I'm gonna talk next. Okay, so I erased this part. Yeah. So yeah.
your Hamiltonian is not Hermitian, so is there any chance at some point of hx and hz the Hamiltonian stuff being diagonalizable?
Yes, right on this point, you can't diagonalize the Hamiltonian. But away from this point, either a bit to the left or a little bit to the right, then you have all the eigenvalues equal to the dimension of the Hamiltonian.
Okay.
Yeah. Okay, so I'll just say, okay, so the criterion of the critical HZ, we could define it with like, okay, so could be defined as the following. So we can define pseudo-critical point of H star Z, that is where they merge, like where this happens, as a function of n. And then we can have H star Z of the ratio kind, which is also a function of n, given by, if you measure a bunch of ratio of eigenvalues, so say identify some eigenvalue to be the stress tensor and some eigenvalue to be vacuum, you can always do this. And this is supposed to be the space-time dimension in the thermodynamic limit at the critical point, right? So then at finite n, this is just our definition of what the critical point is. But then we found if you extrapolate to thermodynamic limit, then these will approach the same value. Ratio, merge. So this is why I say all of them merge at the same point, because the gap closes roughly at the same point at the critical point, and then all of them become composite conjugate pair. Okay, so now let me just like jump to, yeah. Okay. Okay, sure.
Sorry, can I ask one more question about this? So you're saying the gap closes, but aren't you working like on the sphere and everything, and
yeah,
and
but
you have
like
this
n goes to
energy
infinity, the volume of the sphere is going to infinite, so yeah.
Yeah, but like to get these energies, you're removing this factor of the radius of the sphere, and then you're getting the energy, like the energies which tell you what the what the scaling dimensions are, right?
Yeah. But
And
they all
those are
have
real.
they all have 1 over a square root of n in front, right? So they all goes to 0 at the same room of like 1 over n width, right?
Okay.
Yeah. So the width of like this some collide first and some collide later is gonna all happen in a room that's shrinking as the volume increases.
All right.
Yeah. Okay, so this is basically how we treated the quantum Hamiltonian. So then what we did is that we so we can study first of all kind of like how these eigenvalues go from the Ising criticality to something deep in the high temperature phase, and we turn on imaginary field and land at the Youngly criticality and go a little bit further to see all of them collide, all of these eigenvalues collide. And here's a picture of what we get. So we have identity state in the quantum Ising model, and then we increase hx to something in high temperature phase, and then in turn we turn on hz, and eventually this operator flows to the phi because this is the new ground state, and then sigma flows to identity. So it sounds a bit weird, like we should expect sigma goes to phi and identity goes to identity, but since the order is flipped in 2D, which is not going to happen in 3D, so this is the pattern. But remarkably, there's no twist. So yeah, it just operator changed operator change what they mean when you go to 2D and 3D. The pattern is the same. So, and then phi and I will merge. We also have the epsilon, and epsilon flows to box phi in Yang-Li. And then box phi, according to, so according to this picture, box phi is here. And there's nothing near it to collide with, so it's actually going to stay real for a very large parameter space. And then we have T goes to T, D squared sigma goes to D squared phi, and they merge as they're very closely related spin 2 operators. And then we have the box sigma and box epsilon goes to TT bar and box phi, and they merge. Yeah.
Can you and so you have level crossing there?
Yeah, so level cross.
No, I'm
here,
talking about
I guess, well,
I'm talking about
yeah,
stress tensor and
they'll probably avoid each other. Yeah.
I'm talking about the stress tensor and partial squared sigma.
Stress tensor here. Well, on here there's Z2 symmetry, so they do not collide. Okay, sorry, I shouldn't draw this. The Z2 symmetry prevents all of the collision, all of the collision from on this side, and on this side there's really no guarantee. So each time we see the state cross each other, there's actually a very small, merge and recombine, and split. Yeah, but then eventually everybody merge and becomes complex.
Just a naive question. So, and you do it for some HX, and if you do it for another HX, and you normalize things, then you get the same result, right?
If we go to
That's
large
a
enough
check.
n, then we saw the same pattern. Like, at least for these low states that I draw on the board, the pattern stay the same. And then the pattern is also the same in 3D with a little bit of change.
By pattern, you mean the numbers are the same within your precision?
No, numbers will not be the same, right? So these states will just gonna shake wildly, but then who connects to who and who merges who are going to be the same.
I think I'm missing something basic then. I thought that as I approach the Yang-Li line, I get a universal CFT with some universal exponents.
Yeah, this is a little bit past the critical, right? So at Yang-Li, you just get the, sorry. Yes, if I normalize everything, then these numbers are going to be exactly the same. Yeah. I thought you were talking about like these. There's no guarantee that these values will be the same. Yeah. Okay, so then yes.
What determines this dotted line then? Why are you not moving to the right or to the left? Yeah, the location of the dotted line. At what point do you say this is?
We use this definition. The ratio that gives the stress tensor scalar dimension is equal to D.
Okay.
You could change it, and you will make a 1/n correction to everything. Yeah.
But should that not, in some ideal limit, not also be the point where these things merge, where all the mergers happen?
But the mergers always give you the gap is equal to 0, right? So of course you could first go to the thermodynamic limit and find where the merge point becomes in the thermodynamic limit, and then you do everything at that single value of h. We didn't do that because numerically it's very bad behaving. Yeah.
Yeah, but that's your error, right? That's your error in estimating these various exponents, right? Because as you explained, they are the same thing, right?
Yeah, they should be the same thing.
Limit.
Yeah.
So do I understand correctly that in the Yang-Li CFT, the state corresponding to the identity operator is not the lowest energy state?
Yeah, in 2D, only in 2D. Yeah.
So then, but would you say that's the ground state still?
Yeah, I'll say this is the ground state, but this is not the vacuum.
Even though it's not the lowest energy state?
Yeah. If you measure the 4-point function or the 2-point function, you're in the background of phi. You're measuring the ground state 2-point function, but it gives you the 4-point function in CFT. Yeah.
Thanks.
Okay, so then this is basically just dirty numerics. We just study the quantum Hamiltonian at like large enough n, And then we will see, like, for example, if we measure delta phi as a ratio between phi and identity normalized by d phi minus phi, then we see something like the following. We measure a bunch of points, and we use a power law to extrapolate it, and then we get the value, 0.214, roughly speaking. So this is our measurement. So this is in 3D. So our prediction of, okay, let me just jump to the result of these critical exponents. Yeah, so delta phi is at d is equal to 3 is 0.214, and delta phi cube, we can repeat the same thing for phi cube. We get 4.613. So this is a fuzzy sphere, and delta Q is 4.9-ish for the sphere. And then we can also measure like OP coefficients through this overlap. Yeah. A fun fact is that you can also you can also measure the same delta phi from taking this ratio, d phi, d phi, phi, and then phi. And this you can since d phi is just it's just a descendant of phi, that means you can just predict this value from conformal algebra, and it's going to give you let me see. Yeah, so you can predict this thing, and yeah, so it's 1 plus delta minus 3 over 6 delta. Oh, delta actually cancel out. So then what you can do is that you measure this ratio, and then solve for delta. And actually, you will get something like this. It actually converges better than if you measure the eigenvalues itself. So basically, quantum criticality, meaning that you can, so a quantum model means you don't just have the eigenvalues, you also have the eigenvectors. So you can do a lot of experiments. You can measure OP coefficients. You can use the ratio of these matrix elements to do an even more sophisticated check. So this is just one appetizer of that. And more stuff you can do. For example, you can measure the TT phi OP coefficient, which is going to come into 3 polarizations, and they're related because T is conserved. You can check for the conservation numerically and see that this is true. Just as an example of how we did the things. And then eventually, yeah. So finally, I would like to mention that we also did the 4D with a 24-cell regular polygon. So, and then the nice thing about this 24-cell regular polygon is that it's roughly the same, the shape that we can still do exact diagonalization, and the spins are explicit. So we just write down this Hamiltonian on 4-dimensional lattice, and we measure the criticality using this ratio definition of the critical point, and then eventually we get these values. Okay, let me just write them down and then conclude. 4D. 3D we also did. Yeah, so 3D lattice, we have icosahedron, dodecahedron, cube, all of that. Yep.
It's a quantum model, right?
Yeah, it's a quantum model. So we can study 2 plus 1 and 3 plus 1. Yeah. 3D lattice, sorry. 3 plus 1D, 24-cell. From lattice, which is roughly in agreement with the two-sided Pade. And then beyond that, we have 120 cell and 600 cell. So this will be left as a future project whenever we can do it. All right, so I'll just come to a conclusion. We have measured Yang-Lee quantum criticality in various dimensions, and we calculated the critical the scaling dimension of lowest 3 local operators, and we compared the quantum Hamiltonian result and the 6 mass epsilon expansion result, and that they are in pretty good numerical agreement. And taken from this to move forward, I think there are a bunch of things we wanted to study as well. First is we have so nowadays we can construct the K and P the conformal generators, and we can use them to study even higher energy levels. So what's going to happen if you go to higher energy levels is that the states start mixing. So it's very hard to identify which one is primary, which one is descendants, but using the conformal algebras, we can. So we want to do this analysis, and we want to do conformal perturbation analysis to reduce some of these finite size error. And we can also try to improve the Hamiltonian, right? In the first week, we have a very nice lecture from John McGreevy on how to use entanglement and Bootstrap to improve, to get like an optimized Hamiltonian that flows to the IR the fastest. We can definitely do it in 2D and in 3D. How to do it in fuzzy sphere, I think they're trying it. And we have so Yang-Lee is like an example of a large class of models that have this phi cube interaction. For example, M38 minimal model could be extended also to 6D. It's gonna have like a phi cube, let's phi sigma square type of interaction. So it will be also interesting to study this as well as maybe a whole family of different stuff. Yeah, and last but not least, this is non-Hermitian model, but it's not doesn't mean that there's no positivity. We can't bootstrap it. So it will be interesting to start thinking like, what is the formalism of conformal bootstrap with or without positivity in this type of models? Yeah, thank you very much.
So I wanted to ask about the second sheet on the complex H plane. Can you actually probe the kind of away from in a small neighborhood of the Yang-Lee singularity? Can you probe the monodromy structure?
I guess this means that we need to take. I'm not sure. In 3D, I guess. So first of all, I think. In principle, yes, but I think practically it's going to be hard because we need to study so you're interested in the continuous field theory, right? So we need Ising field theory or Yang-Lee field theory in flat space, and that's going to be quite hard because we need to take this and go to the continuum limit. And then make sure there's no curvature or finite volume effect, right? So I think numerically.
In fact, I was worried about another kind of problem, maybe kind of a more severe problem, which is that from the Hamiltonian approach, you may not be able to follow the analytic continuation. I was just kind of curious because it's kind of still a bit of a. I mean, there's some open questions concerning even for the 2D Ising. What happens to this?
So it might be good to first measure a bunch of scaling dimension OP coefficient for Ising or Yang-Lee, and then study it purely theoretically by say conformal perturbation theory or something like that. Yeah, but I'm not sure. Yeah.
Sorry, but but it's related to this question. So for any n, you don't have cuts, right? You just have poles. So there's no second sheet, right?
Yang-Li could be thought of as a singularity in Ising field theory.
No, I understand. From Ising field theory, of course, but from all this, you cannot go away from the second sheet because there's no second sheet. You cannot go away from the first sheet. There's no second sheet, right? You just have zeros.
I think still is possible because so the branch cut is actually here, right? So if you're like a little bit away from the critical point, so if you're this means if you actually so here is the branching point. If you trace down, for example, the gap past this point, you have to make a choice whether you select one branch or the other in the complex counter pairs. So this is your branch cut. So moving to the second sheet means this. Yeah.
So I have two questions. One is about other measurements on the lattice, maybe something like closer to Monte Carlo or these high temperature expansions. Are there independent measurements in d equals 3, 4, 5 that you can compare with or not?
High temperature expansion, I don't know the latest result, but I think our paper quoted one from high temperature expansion.
But Monte Carlo you cannot do because of sign problem. Is that the issue because it's not real? And
yeah, Monte Carlo is bad because there's sign problem. High temperature expansion is like I think general people's approach to this lattice to this classical action. But I'm not sure what is the latest development in that direction. Yeah.
And the second question, you said that these curves, you know it as a function of, you have a 6 minus epsilon expansion, and then you also know it d equals 2 and d equals 1, right?
Yeah. We also know d is equal to 2 and d is equal to 1.
Is there a 2 plus epsilon expansion or a 1 plus epsilon expansion for this model?
Not that I know of. I think it's going to be hard because 2D is interacting, it's an interacting CFT. Expanding around that is probably hard. 1D, I don't know. I haven't seen anything, anybody discussing it. Yeah.
Thank you.
There is this work of Emilio and Apratim where they relate this Yang-Li criticality in d dimensions to so-called branch polymers in d plus 2 dimensions.
Oh.
This is actually a question for Emilio. Is there Monte Carlo for that? Can you do Monte Carlo for these branch polymers? Yeah. And can you get them in 5 dimensions so that you can compare to d equals 3? The numerics.
Well, yeah, there are checks of that, but I think they are not incredibly good.
I mean, why do you have to go to 5D? I mean, we could check for like 2 and 3D, right? So. Yeah,
but 3D Liang corresponds to 5D branched polymers.
Oh, okay. Yeah. I see.